Alright, so this is our final video of analyzing graphs of functions, and then this last one we're going to talk about two very important concepts, and that is even and odd functions. Now before we even talk about this, once we get through this you might say, what's the purpose of ever knowing about even or odd functions? The difficulty sometimes is some of the math tools we learn, we don't get to apply them until future courses. Even and odd functions, as I said, are extremely important. In fact, I teach a junior level electrical engineering class, and on a weekly basis, if not daily basis, when we meet for class, we use properties of even and odd functions and use those for solving engineering problems. So while our discussion after we get done with even and odd functions, you might say, oh, okay, maybe they're interesting, but what's the point of them? As I said, they are very useful, but we use them in future math courses and their properties. So let's go ahead and talk about what an even and an odd function is. Let's go ahead and look at the definitions. So a function f at x is even if for all x in the domain we have f at negative x equaling, come on, equal sign, what's going on here, equaling f at x. Okay, so definition is even, and it's f at negative x is equal to f at x. Now this has a graphical interpretation. This is something we talked about at the beginning of the course. This means you're symmetric about the y-axis. So again, notice how a lot of these concepts keep coming back and repeating themselves. Alright, now we'll learn also why they call them even and odd in a little bit. You might say, why do they call that an even function? There is a reason why they call it an even function. So a function f at x is odd if for all x in the domain we have f at negative x equaling negative f at x. And this also has a geometric interpretation. This means you're symmetric about the origin. Okay, now this is important here. A function can be even, odd, or neither. It can't be a combination of them. Meaning you can't have a function that's both even and odd. You can't have a function that's both even or neither, because neither means it's neither even nor odd. So you can't have that. So you have to have just even or odd, or neither. So we will see real quickly how the names even and odd came about with looking at some examples. But we have to be careful because some people use this as a unfortunate way to determine if something is even or odd. They try to use it as a quick way and you can run yourself into trouble. Alright, so let's talk about how we'll first determine it. So what we're going to do to determine if something's even or odd, we'll evaluate f at negative x and then ask ourselves some questions. First question I always check is f at negative x exactly the same as f at x? If the answer to this is yes, then we're even. So if the answer is no, we go on to the next question. Is f at x exactly the same as negative f at x? Again, if the answer is yes, then that means we're odd. Now, if the answer to both of those questions is no, that means f at x. So let me say if both answers are no, then f at x is neither. Okay, so let's look at some examples of this and see where the name comes from. So let's first look at f at x equals x to the fourth minus 3x squared. Now we're going to go ahead and determine if this is even or odd or neither. And no matter whether we're doing even or odd, we always have to evaluate f at negative x. So let's just go ahead and evaluate f at negative x. Now I'm going to take this in a couple steps here. It's not necessary to show some of these steps here, but I like to do this on the first one. First off, you always need to substitute the negative x in, but you need to substitute it in with parentheses. So it's negative x with the negative inside to the fourth power minus 3 negative x squared. Now this next line here is something that I don't always write down, but to kind of really make sure you see all of this, I'm going to go ahead and do this. So you could write this as negative 1 times x to the fourth power minus 3 times negative 1 times x to the second power. And then properties of exponents says this would be negative 1 to the fourth times x to the fourth minus 3 times negative 1 squared times x squared. That's just properties of exponents. But of course, negative 1 to the fourth is positive, and so this would just be positive x to the fourth. Negative 1 squared is of course positive 1, so I'd have minus 3x squared. Now as far as what I expect to see, I expect to see this line here and at least this line right here. If you want to show these additional steps just to make sure you don't make mistakes, that's fine. Okay, now we've figured out what f at negative x is, and we have to compare this to f at x. Well, I'll just rewrite f at x down here, even though it's at the top. F at x is equal to x to the fourth minus 3x squared. Now, to see if this is even, we have to say, are these exactly the same? And the answer, real quickly, we can see is, yeah, these are exactly the same. So that means I don't have to do anything else, and I know that f at x is even. Okay, so then where does this name even come from? Well, if you look back at the original function here, look at its exponents. We have an exponent of 4 and then an exponent of 2. Those are both even numbers, and so hence we're an even function. However, I don't want you using that as a way to determine if it's an even or odd, because it only works with polynomials and it can get you into trouble if you're not careful. I want us to go through the substitutions of negative x here. Now, you can quickly see, if you think about it here, if we do another example, you can probably guess where the odd gets its name. So if I look at, for instance, g at x is equal to 5x cubed plus 2x, and I want to, again, test for even and odd, well, let's go ahead and then look at g at negative x. Well, g at negative x would be 5 times negative x to the third power plus 2 times negative x. Well, of course, negative 1 to the third power is still negative, so this would be negative 5x cubed minus 2x. Now, clearly we can see this is not the same thing as g at x. I've got negatives and positives here, so this is not going to be even. But let's test for odd. In order to test for odd, we need to know negative g at x. Well, negative g at x is negative parenthesis 5x cubed plus 2x, which the easiest way to look at this is to distribute that negative, so we'd have negative 5x cubed minus 2x. Now I'm supposed to compare, because I'm testing for odd, this, which is negative g at x, to g at negative x, and see if they're exactly the same. Well, clearly they're exactly the same, so that means g at x is odd. Now again, if you look at the exponents here, you can see that you have both odd exponents here. So a 3, and then the exponent here is 1. And I want to do a couple more examples here to really emphasize this. The next one I want to do is a case where we're going to get a neither as an answer. So we have h at x is equal to 3x squared plus x. So then let's go ahead and compute h at negative x, which would be 3 negative x squared plus negative x. Well, negative 1 squared is positive, so this would be 3x squared minus x. Now right away we can see this is not even because it's not exactly the same. I have a negative here and a positive here, so we're not even. But then if I want to test odd, of course I need to know what negative h at x is, which would be negative 3x squared plus x. So then we'd get negative 3x squared minus x. But then we can see that these two are not the same either, because we have a negative here, and then this would be a positive right there. So we're not odd either. So h at x is neither even or odd. Now you might say, oh, that's pretty obvious. I've got an even exponent and an odd exponent, so it can't be just even or just odd. But this is where you can get in trouble. I want to do one more example here and show where you can get in trouble with these things and why you really just need to substitute in. Okay, so let's look at the following one here. So let's look at f at x is equal to 3x to the fourth over x cubed minus x. Now, if you applied the whole, oh, look, there's both even and odd things here, you would say, oh, it's neither then. But that's not going to be the correct answer. Let's see what we get. So let's first evaluate f at negative x. So f at negative x is going to be 3 times negative x to the fourth power over negative x to the third power minus negative x. Okay, so this is going to be, well, x to the fourth, that's still going to be positive. So this is 3x to the fourth over, then this would be negative 1, so it would be negative x cubed plus x. But what I'm going to do here is I'm going to notice this denominator. I'm going to factor out a -1 there. So I'd have negative times x cubed minus x. And then what I'm going to do is that because I have a negative, I could rewrite this as negative parenthesis 3x to the 4th over x cubed minus x. But wait a minute. This is negative f at x. So f at negative x is equal to negative f at x, because what's inside here? What's inside this is just exactly f at x. But then I have a negative on it in front of it. So this function is actually odd. Even though you might guess that it's a neither. Another good example here, I won't go through it, I encourage you to do this example on your own, is look at the function g at x equals x cubed over 3x cubed plus x. Now, your first temptation might be to say, oh look, all the exponents are odd, it's odd. You'd be wrong again. This is an even function. So that's why just relying on exponents is a bad idea, because it only works in some special cases, and those special cases are polynomials. So in general, what do we want to do? And it's what's required. You need to substitute in negative x and see if, for even, does f at negative x equal f at x for even. And then for odd, you need to substitute still negative x in and see if it's negative f at x. And then that would be odd. All right? So this wraps up our dealing with some of the analyzing of graphs. We're still going to be looking at graphs of functions throughout the videos here and throughout the semester. In fact, the next video is still going to be on graphs of functions.